Meeting is started on TeamViewer. Okay, so really quickly, just want to go over this concept of clock gating again. You have this, so we'll start here. Oh no, we did 411 already. So clock gating, you have a clock that enables a latch. In order for it to actually be activated, it has to go through this certain logic. So when it's 0, it'll go onto the gate, and then when it's 1, it'll be ANDed and then propagated through. And so the whole goal of this is to reduce power. So then I showed a couple things about RTL clock gating and sequential equivalence clock gating at the graduate level. We talked about, we had a Kogi stone adder here, where we showed how clock gating was used to minimize power consumption. You can see the difference. And then people made a lot of crazy computers in Minecraft. So voltage and frequency. So what is the dynamic frequency equation? So if the power consumption dynamic, what's that? One half. No, this is dynamic power consumption. But I even gave you guys off on Wednesday. Every time I say this equation, I say it's a pretty classic one. So, yep, you're on the right track. Yeah, exactly right. Just trust your instincts. I'd rather you get, this is the opportunity for you to be wrong, right? 1/2 CL VDD squared. And then you cancel out frequency, and that becomes energy. So what happens is voltage and frequency are often used, since they're both either directly proportional to the power consumption or quadratically proportional. These are good ways to reduce power consumption, right? So this is where quadratic effect on dynamic power. So ultimately, we had chosen a lower power supply. But what were some of the issues? Remember this big question I had you guys try to answer? And so does anybody remember what that was?
The whole, you have to take account for other transistors in series.
Mm-hmm. You have to, exactly, when you're doing transistor sizing, you have to make sure that you actually reach the threshold voltage, which creates the inversion region. So that's where your trade-off in sizes and power consumption comes into play. So mitigate non-ideal transistor effects. So one thing that's done is we're going to talk about this concept of voltage domain. So it's 4.12. So what this means is so let me read the exact definition. I'll tell you what it means as you're writing it down. A voltage domain is an area of the circuit where the supply voltage is optimized for the specific needs of the circuit. So in some areas, when your transistor sizes are smaller, you can actually have a lower voltage domain than the supply voltage. What ends up happening is your supply voltage, which you could have a different voltage domain, can actually drive it. So you have to have some sort of step functions in order to be able to account for it. So basically what happens is, let's say the supply voltage is 1 volt, so it's like a 22 nanometer, and you have some sort of system on chip here, and then it's actually driving. You can actually have a 0.8 volts here. So that reduces your power consumption, right? So it actually has, 0.2 squared, 0.144 watts, because that ties into your power consumption. So typically here, so ensure cell stability, anything where you're trying to restore the power or memory where you actually have to maintain values, you're typically going to have a higher supply voltage. However, for the actual processor itself, you would require a medium low power consumption and a low voltage for I/O peripheral. So why do you think there's a medium voltage for a processor? as opposed to memory? Think back to 385. Even if you didn't have me for 385, you'd still be able to know why this is. What's the difference between a processor and the memory? That thought where you're starting to go, just to say it out loud. This is your opportunity to be wrong. It's better to. This is supposed to be a discussion. Let's hold off on lecture for a second. One of the things I think I said this last class, but I'll say it again. One of the things I fight against with students is that students tend to have this idea that professors are always up to tricks and we're always out to get you. And in some cases, some professors, let's face it, are. I can name more than a few. And I don't do trick questions. I'm always trying to lead you to the most efficient answer. So I think there are more than a couple of you who were freaked out by my hint on number 5 on the take-home exam. And you're like, oh, this can't possibly be this easy. If you're having that thought, I'm trying to lead you to a right answer. I don't do trick questions. In this case, when I'm asking for discussion, I am in no way, shape, or form attempting to shame you. This is the room where you are permitted to fail. No one's going to judge you. No one's going to care, right? I don't have a little list of, okay, well, Mike Malloy said something in 385 and it was wrong, and now I'm going to hold that against him forever, Right. So all those, so I saw like 5 or 6 of you about to say something, and then I kind of go, it's okay. I'm not going to judge you. It's not going to count towards your grade. The key thing is, if you say it, there's odds are good that somebody else is thinking it, and they might be thinking that correct thing or incorrect thing as well. So it's supposed to be a discussion. So when I say something like, why do you think a memory requires higher power consumption than a medium-sized processor as opposed to just lower voltage for I/O peripherals? I want you guys to just take educated guesses. I don't expect you to have a PhD level of competence. That's why you're taking the class, right? So if you're taking the class, by definition, you don't know everything. So I just want you to take what you think you know and have a discussion. Does that make sense? So don't feel judged. Don't feel like, it's not like Demba's going to judge you or Josh is going to go, he didn't know how ALU can do, oh, shame. None of that's going to happen here. So I want you to feel more comfortable. This is taking failure. It's constructive failure. So I want a couple of people to take a shot at this question again. Why do you think this is?
Memory takes up a lot of space.
Memory takes up a lot of space. That is one thing, correct. But what are some other reasons? So memory takes up a lot of space, but specifically, why does it take up a lot of space? Think back to transistor sizing. What is memory? At its most physical level. I'm giving you a hint right here by going in a circle. State machine. There's another word that state machine loops. There's what starts with an S. But the memory does store information. But that ties into that's like the next step. So keep that storage in mind. But there are
synchronous?
Yes, sequential, synchronous, right? And so there's synchronous and asynchronous. So synchronous actually requires more size. So especially when you're dealing with a processor, you have to be able to store a lot of information, and you have to maintain the integrity of that signal, which is why the memory is going to be certain sizes, because it's going to constantly loop, and it has to refresh and make sure that you're keeping that power, right? So that's why you're going to have the highest possible supply voltage, because every time it refreshes, it has to be raised to the optimal signal. You can't lose information, otherwise you can't guarantee it. So in that case, why do you think, compared to a medium voltage for a processor, so this word started with an S, there's another word that goes along with it, starts with a C. So if sequential ties in with memory, what is C? It's the opposite of sequential. Or if sequential is a loop, and then if it's just a straight line, it doesn't have a loop. It doesn't have feed. Combinational, concurrent, it's right along the right idea. So why would combinational logic require less voltage than a sequential element? And it ties what George said and what Josh said into one right answer. About memory, the size, and storage. What are you not doing in a processor? Storing. So what are you doing? Yep, you're taking it in, doing some sort of calculation. So that means you just want it to flow. You don't have to worry about feedback unless it's an arithmetic logic unit. That's why your arithmetic logic unit, remember like the 5 stages of the data path, and you have the biggest one's typically going to be your ALU. The loop back is typically for multiplication. So what your MIPS, right? And remember, one of the objectives of MIPS is high performance execution of compiled code. So they're trying to so basically, instead of doing multiplication, they just do a number of efficient additions and bit shifts. Same thing with subtraction. They have various division, multiplication, or division algorithms. They don't have a divider, so they can reduce that. So basically, all they're doing is they're using the memory in the registers as a temporary storage for sequential elements. And then low voltage for I/O peripherals. So think back to the last example from section 3, where you had all those inverters. What were remember we had the different inverter sizes. We had to figure out like what the proper buffering is to have the appropriate logical effort. So what was the goal of that design? What were they driving? Letting Trey go through his notes, he'll get them to the right answer. And this is typically whenever you have a series of inverters driving something, what Trey is going to tell you is going to be that. So it's going to be driving if you're going to school, in elementary school. Yeah, there you go. It's a bus. Dem was like, I'm just going to wait on everybody. Then I'm going to, right before he comes in, I'm going to fly in with the right answer. Right, anytime you're driving a bus or an I/O peripheral that requires some sort of bus, that's what you're going to be using inverters to do. So typically, all you need to do is try to reduce the logical effort, come up with that, and then you just find the minimum voltage you need to actually hit the threshold, right? Does that make sense to everybody? All right, good deal. And here we have voltage domain examples. So this is a figure from your textbook. So this is an example of when you have a high voltage driving a low voltage domain as opposed to a low voltage driving a high voltage domain. So from the figure you can tell they have a giant X and says bad. That means don't do that. So here, and this is actually a good exam type question. Yeah, hint, hint, wink, wink, nudge, nudge. Where, a good interview type question. So why do you think this would be the case? So here you have some sort of lower supply voltage, and you're going to have these regions, and you're trying to get to a certain point on these voltage inputs where you actually have to drive your inputs at the gate. So when you are remember all these equations you have for current, and you have to have meet a certain region in order to stay out of saturation. So what ends up happening is if you do it this way, where you're not able to actually meet the high and low voltage requirements, and you have a higher, so let's say this was 0.8, right? And it's going to meet 80%, right? So this is 0.8. And it gets to 80% out here, so it reaches, so it's 0.64. But it reaches, let's say this is 1 volt. So in order to reach your noise margin, you have to get to 80% again, right? So it's 0.64 here. And even if you reach 100% of the input value, it's not going to get there. So you actually could go through a whole proof where you're talking, remember that you had the ID is going to be equal to beta, and then you have VGS minus VT, over VDS over 2, right? And so what's going to happen is you can actually justify using this equation that if your VDDL, you could say 0.8 of VDDL is equal to VG, right? And you need, so if you're inverting and inverting again, you're actually trying to reach these noise margins. You can actually justify that by not, even if it stays in the noise margin for the voltage domain on the left, that there are situations where you cannot guarantee that it'll hit the noise margin on the right. Whereas on the other way, if you use the same equations and it's even reaching the lowest level of those noise margins, it'll still work and it'll meet all the requirements so you don't hit saturation. So in this particular case, cutoff is going to be always cut off when it's a 0, when you want the transistor off, which is what you want. And linear is when it's actually working. This situation here is where you're actually going to have a situation of saturation. So a good interview exam type question is, why justify physically using justify physically why a voltage domain of a lower voltage cannot drive a voltage domain of a higher range. And so you would go in that step that I just came up with there. So
What is the example number?
There is no example number. I just came up with.
Okay.
Yeah, this is just I'm going over lecture thoughts. Yeah, so the question becomes, and this could actually 413 could be the second part of this question. So part 1, here's a good way of phrasing it. Part 1, can a voltage domain of a lower voltage drive a higher voltage? Yes or no? If no, why not? Actually, you know what? I hate those kind of questions. Those are trick questions. Okay, so I'll say, yeah, I'll just say, we know it is known that a voltage domain of a lower voltage cannot drive a voltage domain of a higher voltage. Justify physically. So you could use that equation, and then you can actually describe the underlying physics. So if you want to go even further detail, you say, well, okay, so you have this saturation equation, right? And then you would talk about how, well, if you don't meet these equations, here's what's physically going on underneath. You hit saturation, so actually your inversion region gets pinched off at the drain. So you're not actually, by not meeting that noise margin, and you're in saturation mode, you get pinched off. So it's actually not going to work, even though you're doing that. So then the second part would be 4.13. How do we convert? So it's known that you can't be done, but let's say you have a bus that goes into another portion of a circuit that then takes everything and loads it into memory. So it's like store word, right? So you have a bus coming from an ALU, and it circumvents the ALU and goes into data memory, right? So that's a 32-bit bus. So I have to go from a lower voltage to a higher voltage. So what's actually going to end up happening is we use this level converter. And so I would actually follow that up with 4.13 and say, all right, so here's what's happening. I have 2 inverters. I got 2 PMOS and 2 NMOS transistors. I actually have a third one here, right? And so I'm going to have 2 supply voltages brought in. I'm going to have VDD high and VDD low. And what I'm going to have is I'm going to have my input, right? And then I'm going to have X and Y on these signals here. So this is a 6 transistor cell. So here's what's going to happen. The VDD high is tied to both PMOS circuits, because ultimately we'll want to drag it up to that higher supply voltage. And then VDDL is only driving this inverter here. So we have A input, which is tied to this NMOS transistor, and we invert that signal and put it on the NMOS transistor here. So when A is 0, N1's going to be off, and N2 is on, because we've inverted it. N2, so now that this is on, it's going to pull Y down to 0, which is going to turn on P1. So here's 0's here. Well, look at that. We got on that PMOS, right? So now guess what? X is going to be 1. So that pulls X up to VDDH and ensures that P2 is off. Because here it's 1, and then that's going to turn that PMOS transistor off. So we have a strong 0 that meets the noise margin for VDDH here, and we have a 1 that meets a strong 1 for VDDH there at output X. So here's what happens when A is 1, so that's the opposite value, right? That means that N1 is on, right? So that means X is going to be 0. So we're going to have a strong 0 on the output there, right? And that's going to put 0 here. That means P2 is on. That means Y is going to be 1 on the output. Which means P1 is going to be off, which is going to make this a strong 0 for the appropriate supply voltage for VDDH here. And it's going to be a strong 1 because what's going to happen is this one's going to be inverted to 0. Now it's going to be on. That's going to be, and that P2 is going to be on there. So what ends up happening is we use X and Y as our restored output. So we have a restored 0 and a restored 1 no matter what. So when A is 0, that's going to turn that N1 off. It's going to turn N2 on because we have this inverter here. That means it's going to have a 0 at Y. Right? So Y is always going to match A. And X is going to be the inversion of A. So that means if we have a 0 here, by following this circuit, we have a 0 here. That turns on we have created an appropriate inversion region. We're going to put X on this output. That means we're going to have a strong 1 here that meets our noise margins for the high supply voltage. Likewise, if it's a 1 here, it turns P2 off. And that strengthens the 0, which means it's more than likely to meet the noise margin for Y. So therefore, you can have appropriate signals for both a 0 and 1. And therefore, you have appropriately converted the level. Does that make sense? All right. Okay, so you can probably put together this concept of dynamic voltage scaling. And what that means is, so we know that we have voltage domains, and we also know that we use, we also want to have voltage clocking, right? So you want to be able to only have your voltage running at certain times when you're actually going to be using the circuit. Otherwise, it's just off. So here's the challenge. Many systems have time-varying performance requirements. So, and you guys are going to start going into SPICE coming up here after the break. A workstation requires more performance when running SPICE than when running Solitaire. And the reason why is SPICE is actually a simulation tool simulating a circuit, whereas Solitaire is just a basic graphical user interface with minimal memory requirements to be able to run a card game, right? So what happens is we actually need to be able to tell the circuit when it requires more power and when it does not. So you actually need, in order to put the appropriate supply voltage into the circuit, we're going to use this concept known as a dynamic voltage scaler. So we formally define it as dynamic voltage scaling as a process which saves large amounts of energy by reducing the clock frequency to the minimum sufficient to complete the task on schedule. And so in section 6, we're going to go into a tremendous amount of detail as to how do we determine that schedule. Then reducing the supply voltage to the minimum necessary to operate at that frequency. So remember, we have power is 1/2 CL VDD squared frequency, right? So this whole concept of dynamic voltage scale is find me the minimum here and find me the minimum here. And therefore, by definition, this should be the minimum amount of power required, right? Can't go any lower. I need some sort of output load capacitance that's inherent to the design of the circuit. Therefore, I need to figure out your minimum supply voltage and minimum frequency. And so the way this is done, so this is the TGO. So we have this dynamic voltage scaler controller, right? And it has a number of different inputs and outputs. So we have some core logic, which is actually what we're trying to run. And it's actually going to measure the temperature and the workload. And then our two inputs, we're going to have our voltage controller. And then we're going to have our max supply voltage, right? V in. What?
Is that diagram for?
No, that's why I put this here.
Okay.
Yeah. So you have your maximum supply voltage. And what's going to have happening is your voltage control is going to take in how much work you're doing, what the current temperature is, and we'll get into PVT corners later. Power, voltage, and temperature. And you determine the minimum amount of frequency and the minimum supply voltage to get it done. And the DVS controller uses all this logic. So this is just a basic overview of how it works. All right, so as we add to, as our transistor size gets smaller and smaller, we have to worry about static power consumption more and more. So we started using all this dynamic power consumption. We used, dynamic voltage scaling to try to get the minimum amount of power consumption to run the circuit appropriately. And our trade-off is the more we have to do, the more we add to the core logic. So that diagram, everything we're adding to the area is our dynamic voltage scaling controller, our switching voltage regulator. Before it was just this core logic, right? So we're reducing power, but our circuit's getting larger and larger. So we try to trade that off by having reduction in transistor size. Well, what's going to happen is we start having to worry about this static power consumption. So before 90 nanometer mode, we had to worry about, we just basically said it was sleep mode because it was negligible compared to dynamic power. In nanometer processes with low threshold voltages and thin gate oxides, remember that's SiO2 in between your gate and your bulk, leakage can account for as much as 1/3 of the total of active power. And this is because we start having to worry about this subthreshold current. And we have our gate source voltage, remember our body coefficient, drain source voltage minus VDD, S. I can't remember what S is. I feel like that's stack effect, but I think it's stack effect. When I email everybody, I'll try to remember what S is. Shows you how rarely I actually use that equation. Was what? Laplace equation. I see Dr. Daigle's making you guys work hard, I see. I'll look it up. I apologize for not knowing. But the next concept we are covering is stack effect. So the idea behind stack effect is what happens when you start having this leakage current going through multiple transistors, right? So we know that we have to put a 1 on the NMOS transistors to turn it on. So in this particular example, we have our transistors off. So what's going to happen is the stack effect is the instance where leakage through 2 or more series transistors is dramatically reduced. So you have a certain amount of leakage current, or leakage current is its ability to get through even though there's not much of an inversion region, right? And now I need to get through yet another one, right? So 4.5 here, we're given the circuit to the left, with both transistors off, demonstrate how the stack effect reduces. So we're talking about how we have the drain is at VDD, right? So we've tied VDD to this set of NMOS transistors. So we have a 1 here. So the stack is going to leak because we have our source, and we're trying to compare it to Vx, which is our drain, which is also going to serve as Vx. So the drain voltage here is going to be 0. So we're going to start tying these into our equation up here. So we use this equation here from 4.15, the subthreshold currents. We go all the way back to Kirchhoff, right? We know that the current through both of them is going to be the same. So our subthreshold current is we're actually going to plug in the numbers for both of these, right? So we're going to assume that base VB is going to be 0, right? So that just becomes our source. And then we just plug these numbers in, right? So VDD is going to be VDD here. So this is N2. So gate is going to be 0, and source is going to be 0. So that just goes away, right? So source is going to be 0, and our base is going to be 0. So this is going to go away. So that's how we get Vx, which is this value we're trying to figure out here, minus our supply voltage, which is this from this part of the equation. There. So see how that equation is derived? So you're just plugging in those numbers there. And so that has to be equal to the current going through this transistor as well. So we're going to this equation. We know that Vx is our drain, here, right? And then we know gate is 0. So we have negative Vx. Vg, remember Vgs is equal to gate minus source, right? So if gate is going to be 0 and Vx is gate, that's how we get negative Vx, right? Does everybody understand how we get negative Vx there? Okay, a lot of the head nods. So now we start plugging this in. So VDS, 0 and Vx, right? VDS in this case is going to be 0. So VDS is going to be 0 minus Vx again. So that's how even though it's negative Vx minus VDD. And then here, Vx comes from source base, right? So source And then the base voltage is assumed to be 0, so that just becomes minus body coefficient times V of x divided by S. And then we set these two equal to each other. And then you can make this simple by, these two are going to cancel. And then you can do log base 10 of each side. Right? And so that means S is going to go away. So then what we're going to see here is this next equation, where it's going to be right? That's from here. It's going to be equal to negative Vx plus N, this quantity here. And then when you solve it, it comes out to this. So we have our body coefficients, our values here. Went a little too far. So therefore, as the ability of the N2 transistor to regulate the change in voltage rises, the gate source voltage for N2 becomes negative, reducing its leakage. So what we're saying here is, by stacking these transistors like this, it reduces the amount of leakage current. So I'll read this. The drain of N2 is at VDD, so the stack will leak. However, the middle node voltage Vx settles to a point where that each transistor has the same current. If Vx is small, N1 will see a much smaller drain-induced barrier lowering effect and will leak less. As Vx rises, VGS for N2 becomes negative, reducing its leakage. Therefore, since the current through both transistors is the same, we can determine that, and this is the equation that we just walked through. And so here, this last portion, we're just plugging the value back in, right? Here. To reduce it, it essentially becomes that, right? It becomes this, and then it's approximately equal to just this value here. Because if you put in N VDD over 1 plus 2N body coefficient minus VDD, then you just put these in the numerator or denominator, you subtract, and you get that. And you pull VDD out, and then that's approximately equal to that. Okay, so does anybody have any questions about stack effect? Okay, so the next challenge that we have in power consumption is this concept of gate leakage. So gate leakage occurs when carriers tunnel through the thin gate dielectric when a voltage is applied across the gate. So we put a voltage on the gate, right? We have this gate here, and then we have this dielectric too. SiO2, not SiO3. And then you have, you have a source and a drain, and you have a transmission region. So gate leakage. So carriers come through here, they get through this thin dielectric, and they go, nope, I'd rather go this way. And it's a function of this thickness of this oxide and the gate source voltage, right? So you have VG, VS, TOX, right? So this, as our transistor sizes get smaller and smaller, this becomes a bigger and bigger issue. So at larger transistor sizes, this is virtually a non-issue, because when you had it scaled, your thickness of your oxide was sufficient to keep this from happening. But as we get to smaller and smaller, remember that diagram I showed you at the beginning of the semester where I showed you a 0.25 micron process, and the transistor was about this size, and then I showed you a 22 nanometer at the same scale, and it was like that. So electrons aren't getting smaller. Electrons are always going to be the same size. So that means you had a much bigger, as opposed to much smaller dielectric, right? So that's where making everything smaller, as transistors get smaller and smaller, we start to discover little issues like this that didn't come across before. So an order of magnitude less for PMOS than NMOS. Why do you think that is?
Because PMOS are normally bigger than NMOS, correct?
Well, the reason why PMOS is bigger than NMOS is a function of the reason for this. Why do we make PMOS bigger than NMOS? Yes, exactly, right? So what is the primary charge carrier? Electrons or holes? Electrons, right? So therefore, we just have more electrons because they're the dopants, and the holes are when the electrons move back and forth, right? So therefore, you're actually going to have more electrons punching through. The holes are just when you had an electron go over here and go over there and fill one, and therefore you get a hole back here, right? So therefore, it's an order of magnitude less for PMOS than it is for NMOS. So here we're talking about, we start talking about high K dielectrics. So basically what we're trying to do is regulate the amount of the oxide thickness while also ensuring it's properly doped. So what ends up happening is this 3.3 voltage, that's where we started having 0.18 volts, 0.18 microns as our transistor size. So everything below that is going to start dealing with less 3.3 or less, right? So, 22 nanometer with 0.91 volts, I think. And then as it gets smaller, you're going to have smaller transistor sizes. So you start having to work with these different oxide thicknesses. And so by also limiting the supply voltage, which we're already doing by trying to use this dynamic voltage scaling, right? So dynamic voltage scaling, we're trying to find the minimum VDD and the minimum frequency required to do this, right? So if you have more switching, you're going to have more switches between whether or not you have an inversion region, which creates more opportunities for gate leakage. So if you limit the frequency and you limit the supply voltage, you can ultimately control this voltage. So here we have a really big example question where we're going to tie in equations from that you thought disappeared when we left section 3. They're back with a vengeance. So here we have so this is kind of building on an example question from before. So you have a digital system on chip with a 1.0 volt 65 nanometer process. Remember, we have 50 nanometer channel lengths, and we have lambda is equal to 25 nanometers, right? And it has 1 billion transistors, of which 50 million are logic gates and the remainder are memory arrays. Sound familiar? The average logic transistor is 12 lambda, and the memory arrays are divided into banks, and only the necessary banks are activated. Or not only the necessary bank is activated. So you have all these banks, and only one of them is being accessed at a time. And the average memory transistor is 4 lambda, and we have a switching factor of 0.02. So up to this point, we've the same question as before. So now we're going to start adding sub-threshold leakage for off devices is 100 nanoamperes per micrometer for low threshold devices and 10 nanometers per micrometer for high threshold devices. Gate leakage is 5 nanoamperes per micrometer. And so we've also added this junction leakage is negligible. Memories use low leakage devices everywhere. Logic uses low leakage devices in all but 5% of paths that are most critical for performance. So now we have 1 billion transistors, of which 50 million are logic gates, and only 5% have this high threshold devices, right? So we can start seeing how we're going to put that into the equation there. Estimate the static power consumption. So here we have we're going to figure out our widths for low and high, right? This should say high and low, sorry, high and low. So here we have 50 million, right? And that's 5%, right? And they're all 12 lambda, which is where this value comes in. 0.025 micrometers comes from here, times 5%. So the width of all the transistors that are using, this should say high and this should say low. This is a typo. And so for low, it's essentially the same equation times 0.95 because we're using these low threshold devices for all but 5% of them, right? So that becomes 95%. And then we have 1 billion minus 50 million here, which represents the number of memory elements, times 4 lambda, which comes from here, times our feature size, and that comes out to 109.25 times 10 to the 6 micrometers. So plugging this into our equations, right? So we have our low and high, right? So I did put it in right. 0.75 from here, and we got 584 microamperes because we're multiplying it by our actual subthreshold leakage. Hold on. Let me minimize this for a second. This is not right. Here. Here we go. So this is actually high. This is low. And so this should be 10, and this should be 100. And this should be 10, and this should be 100. So does everybody have a calculator on them? So this is 10 to the 6, 10 to the negative 9 microamperes come away. So this should be 10 to the negative 3. Let's start 10 to the negative 3 here. I gate is correct. Let me close this out. Did I do that right? Okay. Just wonder for low threshold. Wait, hold on. Did I have that? I had it as 100 before, right? So, okay, so that should just mean that. No. So trust my gut the first time I do it, right? The math's going to come out correct there. So it's for 100 nanometers for all low threshold devices. And so that was 109.25, so that's this one here. And the high is this value times 5%. So now this equation is right. So my first edit was. So can I get the cover? So what happens when you do your own notes? So this is 7.5 times 10. That's 7.5 times 10 to the 6 divided by 10 to the 9. So that's 10 to the negative 3, right? Plus 109.25 times 100. Times 10 to the 6 times 10 to the negative 9 is 10 times 10 to the negative 3. Equals 10.925 plus 32, right? So the nanoamperes, micrometers cancel out, the nano canceled out, nano canceled out. So this is just, oh, and this should be divided by 2. .466. Oh, milliamperes. It's 10 to the negative 3. Okay. Make sense? Thank you. And so let me do save, and let me do save as VLSI 2014, PDF. And so now the notes are correct. All right.
down the C static, which one?
Yeah. So instead of 859 milliwatts, that becomes should come out to 275 plus 5 isn't that hard. All right. Okay, so 4.18 here. This is basically we're going over how the stack effect impacts circuit operation. So in this case, we're doing a NAND 3 circuit, so we have a 3-input NAND gate. And so all 3 MOS transistors are off, and the triple stack effect cuts the leakage off by a factor of 10. And so what this table here is going to show is what's actually driving your Vx here. So Vx is the voltage in between N1 and N2, right? And so that is V2 is what, or Vz is here, and then Y is our total output, right? So we have subthreshold current, gate current, and total current. So when our input state is 0, 0, 0, our subthreshold current is the smallest. You see how it's, all of them are, and we're actually getting different values based on which one's coming in. So A, B, and C, so this is A, B, and C. So here we have a 100 nanometer process for a 3-input NAND gate, where the gate current for NMOS transistors is 6.3 nanoamperes. Our gate for pre-MOS transistors is 0. Our off for NMOS transistors is 5.63, and our off for PMOS transistors is 9.3 nanoamperes. So when you have 0, 0, 0, it actually comes out to 0.4 volts because all 3 of these are off, and all 3 of these are on. So that makes it the difficult here. So that's all sub-threshold current. There's no gate current because we don't actually have any gates on. So here we have 0, 0, and 1, right? So you're going to start to see Vz change, right? So Vx is going to be 0 because of the stack effect, right? See how they're both cut off here? The reason why in this portion of the table they're both stack effect is when you have 0, 0, 0, the stack effect affects here, and it also affects here, right? So you put a 1 here, and these are 0. Well, now you're going to have VDD, which is on the output, minus the threshold voltage of an NMOS transistor here. And then you're going to have stack effect affecting this. So you're going to end up having subthreshold current where you're not actually going to have current flowing through this circuit, right? So when you have 0, 1, 0, this is where things start getting interesting. Notice how neither of them are the stack effect, right? Because we actually have an on transistor. and 2 off transistors. So there's no stack. So when we have 1, 1, 0, that means this transistor's on, and this transistor is off. So you can see VDD minus T is actually driving this. And what ends up happening, and these are numbers derived through experiment, you're actually going to have a significant amount of subthreshold current, and you're going to have a total current of 10.1. And this is from chapter 4 of your textbook too, this table. So what happens when you have 1, 0, 0? You're actually going to get a stack effect for VZ because it's here, right? So that should, yep, it's there. Right? Does that make sense? And now you're starting getting a subthreshold current because it's still off, and you're getting gate current because you're starting to get, it's not, this hasn't been cut off the whole time. Now now the rest of these, you're actually going to have some pretty substantial gate current. I'm sorry, up through here, you're not having much gate current, but here you're going to have substantial gate current because you're starting to get through here. So 1, 0, 1, stack effect is gone. You should have VDD right here, right? And this transistor's on. This is our off transistor. So VDD minus VT is going to impact VZ. And Vx is going to be at 0 because you're having, so see how this is why all of these are 0? Because you're actually going to have a 1 here, and you're going to create an inversion region that's going to get to Vx. And then what's going to happen is you're going to see these two values here for B. That's why you're going to have 0 for these two values, right? Because it's actually going to flow through both of them. So when you have 1, 1, when it's 0, when the transistor's off, you're going to have VDD minus VT driving that, right? So this is going to make it 0 here and 0 here. And then when this is 1, you're actually going to have complete throw of current. So that's why this is your highest current value here in the table. You see when you have the most stack effect, your gate current is basically gone. And you have very low current totals. So the stack effect goes, suddenly your voltage starts jumping, your current starts jumping up. And when you have 2 transistors on, suddenly your total current starts jumping up pretty high, but it's cut off here. So once you actually start getting current flow from your source, then you start seeing all these current numbers really start to jump up. So that means you have activated transistors where one of these in between source voltages has actually reached a inversion region. You don't have the stack effect or immediate going on. So you can see how the whole goal is to get all 3 of these transistors on. And this is a good summation of all of these sub-threshold effects and non-ideal characteristics of the transistors. And so where we're getting all these, if you recall, why are these numbers going up, these sub-threshold leakages? Because we actually have PMOS transistors being off. So what ends up happening is that let's say we have this 1, 0, 0 instance, right? Oh, let's do 1, 0, 1. So we have 1, 0, and 1. That means we have a 1 here, we have a 0 here, and a 1 here, right? So this means we have 2 NMOS transistors on, 2 PMOS transistors off, but we still want a 1 on the output, right? So that means we have a tremendous amount of subthreshold current going on here. We still need this to drive our output. So we have a lot of subthreshold current, and we have a lot of gate current, because we need to have more current flowing through in order to be able to reach our noise margin. Even more so when we have this value is a 0, that means this transistor is on and this transistor is off. But when we have 1 and 1 here, that means this transistor is on, this transistor is on, this transistor is off, this transistor is off, and we still need to reach our noise margin of 1. So we have a good amount of current throwing through here, right? So this is 1, 1, 0. So we have really high subthreshold currents. And we have to have higher gate currents because we only have, because all this, we actually have to drive it down and be able to get this value out from a 1 on the output. So that's why our current is going out even more. So when we go into cadence, and we're going to see how different inputs and outputs have different sizes, and that these, and not different sizes, but different current and voltage values, and that's all in there. In the diagrams for the circuits. This is where that all comes from. So when you design your cells, you have to account for all the possible inputs and how all these currents will contribute to their logical effort. So that calculation of that, that load capacitance ties into being able to make sure that all of these work at appropriate frequency and appropriate supply voltage. So this is another concept called power gating. So the whole idea is you just have a sleep mode. If you say sleep mode is 1, all of these PMOS transistors are off. Once you say 0, all these PMOS transistors are on. And then that means you have a 1 here. That means all of your outputs are regulated with AND gates. So if you have this sleep mode off, that means power is not being consumed by the power gated block, but you are consuming some power here at the PMOS transistors on the pull-up. So the issues here, I probably should ask you, but I'll just read through them because we only have a couple minutes left. So obviously you have to make sure these transistors are sized properly and can ensure that no signal is getting through here. You have to have a delay to make sure that this works. And transition between active and sleep modes takes some time and energy, so timing is important. So let's do 4.7, and then we'll stop here, and then we'll start talking about low power architectures next lecture. So everything up through 4.7. So we're designing a header switch for a power gating circuit we just discussed in a 65 nanometer process with a 1 volt power supply. Suppose the PMOS transistor has an on resistance of about 2.5 kilo ohms per micrometer. The block being gated has an on current of 100 microamperes. How wide must the header transistor be to cause less than a 2% increase in delay? So our assumption, to ensure a less than 2% increase, this virtual supply voltage must drop by less than 2% of VDD. Therefore, 2% of 1 volt is 20 millivolts. So that's where we're going to use to calculate an effective resistance. So we have our voltage effective times our divided by our on current. So we know that the on current is 100 milliamperes, which we get from here. So in order to determine the effective resistance, which is the resistance to get less than 2%, we just use Ohm's law. 20 millivolts divided by 100 milliamperes becomes 0.2 ohms. And since we know the resistance width is 2.5 kilo ohms per micrometer, we can determine the width that we need by just dividing 0.2 ohms by kilo ohms here. These cancel out. And this becomes 12.5 micrometers. So our width that we need for our power gating block is found using that equation. And so this solution here at 12.5, we go to that previous diagram, that ties into how much we need here to get less than 2% delay. Does that make sense? All right, so that is where we will end today.